In the case of an inductor in an AC circuit, what's always true is this expression. VL is L delta I over delta T. Now, like we did for the capacitor, we can define what we call inductive reactance. Notice here the difference. XL is 2 pi F times L. Remember, for a capacitor, it is 1 over 2 pi F times C. And once we have the inductive reactance, we can write the peak or maximum values. We can write them in a relationship similar to Ohm's law. Again, we can write the RMS values as well with this expression. Remember, the inductive reactance is given in ohms. Now, if we compare the voltage and the current, for an inductor in an AC circuit like this one, notice here the voltage is in black and the current is in red. Now in this case, look, the voltage is ahead of the current, and they are again 90 degrees out of phase. So when the current is 0, the voltage is maximum. When the current is maximum, the voltage is 0. So we are going to have it somewhat looking like this. My bad graphing. If we graph the reactance as a function of the frequency, looking at this expression, it is of the form XL is equal to a constant times F. So it's a linear expression, and we should see something like this. If instead we would like to look at the current as a function of frequency, this is what we get. So it's essentially the opposite of what we have seen for a capacitor. We have the 1 over F dependence here, while for the capacitor we found the 1 over F dependence for the reactance. And then for the capacitor we have found a linear dependence for the current, while we find the linear dependence for the reactance for the inductors.